Good afternoon, everyone, and good morning to some. My name is Joe Grabowski. I'll be your host for today, and welcome to our Exploring by the Seat of Your Pants Hangout. For those who don't know, Exploring by the Seat of Your Pants is all about bringing science, adventure, exploration, and conservation into classrooms across North America and hopefully beyond. And I'm really excited for today's Google Hangout. We're joining Daniel Devost, the Director of Science Operations at the Canada-France-Hawaii Telescope. And Daniel's joining us from the observatory headquarters on Waimea on the Big Island of Hawaii. And Daniel is an Exploring by the Seat of Your Pants veteran. He's taken part in many hangouts with classrooms over the last 2 years, and it's always a great time learning about the telescope and the mysteries of the universe that astronomers are using it to try and unravel. So Daniel, I hear it's a wonderful day in Hawaii.
Yes, a warm day again.
Excellent, excellent, excellent. Once again, it's great to have you joining us. It's always fun to be able to host these hangouts, and I think students get to learn a lot about the telescope and just what you guys get up to.
Thank you very much. It's a pleasure to be here.
All right. Well, where are you? Tell us a little bit about where you are today.
So today I'm in the remote observing room in our headquarters at the Canada-France-Hawaii Telescope. So you see all these screens behind me. They're the screens and all the equipment that the observer last night used to gather data and look at the sky and gather data for scientists around the world. So every night we have someone here in this room that spends the whole night, all the way from sunset to sunrise, gathering data.
All right, and so we have a great group of classrooms joining us from Canada and the US today, and extra points because you're Canadian as well.
Yes.
Excellent. Well, Daniel, we'd love to know a little bit about the telescope and just what it is that the astronomers are looking for. Okay.
Thank you, Joe. So welcome, everyone. So thanks for coming to this wonderful program that's the Exploring by the Seat of Your Pants. So I will just start my presentation. I will first share the screen, and you guys should see it.
We got it.
All right, perfect. So let's get going. So today I'm going to talk to you guys about the place that I work, which is called the Canada-France-Hawaii Telescope. And more specifically, I'll tell you about how we do science with professional telescopes on Maunakea. So I'll explain to you the tools that we use, and then I'll talk to you about some of the science that we're doing with these tools. So first, we're located on the Big Island in Hawaii, right in the middle of the ocean, and we're located on the Big Island of Hawaii. So Hawaii is a series of small islands, and we're on the biggest one. We're on the highest peak of the Big Island, which is called Maunakea. It's this peak that's close to 4,200 meters high. It's something like 13,500 feet high. So it's pretty high mountain. There's altitude effects when you go up there. You have a hard time breathing. So the altitude and the fact that we are in the middle of the ocean makes Maunakea one of the best sites in the world for astronomy. And during the questions, if you guys want to know more about that, I can talk about it a little more. So here's the summit of Maunakea with the CFHT call. So there's up there, all doing different types of science. There's mirrors and also some antennas up there at the summit. So for CFHT here, 5 partners can ask for time. So we have proposals from scientists in France, in Canada, at the University of Hawaii, in China, and then in Taiwan. So every year or twice a year, astronomers from these countries and institutions ask us for time. They ask for CFHT time. Only the best programs get time on the telescope. So there's way too many people that ask for times. We only have 365 nights a year, so we have to limit the number of proposals they get on the telescope, and we do that by selecting the best one. And right now, we're right in the middle of this process. We just got all the proposals from all our agencies. We have over 100 proposals, and we're going to look through all of them and rank them and pick up pick the best ones. So now let's go inside the observatory. So the telescope is a 3.6 meter telescope. And when we say a 3.6 meter telescope, that's the diameter of the primary mirror, which is about 12, 13 feet, basically. So it's a big mirror. And this is usually how you estimate the size of the telescope. This is how you gauge telescope sizes. So a 10 meter telescope will be a 10 meter mirror. It's like Keck is on Mauna Kea. So here, it's a 5-story building, and you can see 3 of our day crew members in there. So just to show you how big this is. So this is 1 floor of the 5-story building. So the telescope is on the 5th floor itself. So first, before I move into the science, I'm going to talk to you about instruments. And instruments are really the tools of the astronomers. They allow us to study the universe in a different way. Different ways, sorry. Each instrument is unique, and each have a different way to look at the night sky. So first of all, I'll just introduce you to what an instrument is. The telescope itself is not something that's considered an instrument. It's more the light gathering object that gathers light for us. So this is a picture, a representation of Galileo Galilei observing the sky in the late 1500 to 1600. And he basically had 2 instruments, his eye to observe the heavens and his hand to record what he was saying, what he was seeing. So here you can see one of his drawings. So in 1609, using these 2 instruments, Galileo discovered the 4 moons of Jupiter, Io, Europa, Ganymede, and Callisto. And if you take a small telescope, off-the-shelf, cheap telescope, and you look at Jupiter, you will see these 4 moons. And what Galileo did night after night, he drew their position and recorded it on a piece of paper here. So you can see here, there's Jupiter, and here there's one of the satellites, another one. And then he went on and recorded all of them, and he figured out, and he discovered that they were orbiting Jupiter. They were going in circles around Jupiter. And at the time, that was a major discovery. And that led to his model of the sun-centric solar system. The sun's at the center of the solar system. In these days, people thought that the Earth was at the center of the solar system. So modern-day astronomy, people, use telescope off the shelf, and amateur astronomers use telescopes and commercial cameras to record their data, and they take wonderful pictures of the night sky. The camera itself that you see here, this is what we call an instrument. So basically, this is what we record the data with. And astronomers love cameras, and we do all sorts of cameras, of weird cameras. It's more than, it has way more capabilities than just taking a simple picture. So I'll explain to you the 4 types of cameras that we have, but there's a whole slew of them in astronomy, all different types. So CFHT's instruments, we have 4 instruments, basically, which are 4 cameras. They each have a camera. So MegaCam is one instrument, WearCam, Espadon, STED. So astronomers love to give names to their instruments. So these are the names that were given to each of our cameras we use to observe the night sky. So first, MegaCam. So it's a 6-meter tall camera. So MegaCam, basically what it does, it takes pictures, but it's 6 meter tall. So it's about 20 feet tall. So it's a big camera. It has 377 megapixels that record optical light. So overall, it lays those 377 million pixels on an area equal to 4 times the size of the moon. It thus records a large amount of data within one single picture. This allows us to study large volumes in the universe. So here you see with the moon into MegaCam's field of view. So, 4 times the size of the moon, that's what we call the field of view. So every camera has a field that it records. So for MegaCams, it's 4 times of the moon, 4 times the size of the moon. It's pretty big for astronomy. It's not the biggest. It used to be the biggest camera in the sky, the largest field of view recorder. But now there are bigger ones, just a few of them. Now our second instrument, WIRCam, it's also a large camera located like MegaCam here at the prime focus of the telescope. It means that it's about 100 feet up in the air, about 20, 30 meters up in the air, and it records the pictures directly there. WIRCam records infrared light that is invisible to our eyes. So just to give you an idea of some of the capabilities of WIRCam, infrared cameras record temperature and can see through material that is opaque to the human eye. So here you have two pictures of two glasses of water. On the right, on the left-hand side, this picture here, it's a regular picture taken in the light that you can see with your eye, which is similar to MegaCam, basically. So one contains cold water and one contains hot water. And we could put the hot water in the red glass and the blue glass, and we could mix it around, and you wouldn't know from this picture. However, if you take an infrared picture of it, then I can't fool you. You will see which one is the hot, which one contains the hot water. And you can see here that it's the red glass that contains hot water, and the blue glass contains cold water. So you can also see through things, things that you normally don't see through with regular light. So here you can see someone that's holding a trash bag, and you see the optical picture, you don't see his hand, but in the infrared picture, you see through the bag and you see his hand. And also something else you see is that the skin temperature. You can see how the temperature is on his face and all over where his skin is, where his shirt is, and all of these things. So you can record temperature and see through things with infrared. So let me talk to you about how we do science with cameras. So this is a very simplified schema of a camera. So of course it's not how cameras are built, but it's just to make you understand how things work. So here on the left you have the detector here that records the data basically, and these detectors are the same principle than what's used in a regular camera, the camera you use every day, except it's way bigger. So this records the star images that are coming from the telescope here. So these beams is the light that comes from the telescope through a red filter. So it only filters the red light. So this way, the detector records the intensity of the red light. So we do that with the green light and the blue light, same thing. We record the intensity of each of these colors. And then astronomers like to put things in graphs. So here's how we analyze our data. So for each color, we have an intensity here. We put that in a graph, intensity here versus color. So the intensity here in the blue is lower than the intensity in the green, and in the red, it's even higher. And while you're at it, you may want to add infrared colors, right? So this is all blue, red, and green that you see with your eye, but you could use an infrared camera and then record the same region of the sky and then do the same thing. So you add your infrared colors here, your points, your infrared points. And then what we do, we compare that to our theories. So we all have a grand theory that we want to verify or make sure something's right. So we look here, the black dot here, the black line here is the theory, the model that whoever plotted this data with. And you can see here that the model works pretty well with the blue, the green, and the red, but if you get further out into the infrared colors here, the model doesn't match the observations really well. So something is wrong with the model. So in general, this is how we do science with imagers. So another type of camera that we use is called the spectrograph. So we have a spectrograph here at CFH. It's called Espadon. It's a spectrograph and a polarimeter. I'm not going to talk about this polarimeter part. I'm just going to talk about the spectrograph part. So basically, the instrument is here on the telescope, and it feeds 30 meters of fiber all the way through the camera, which hosts the spectrograph here. All this here, the spectrograph is hosted there. So a spectrograph basically is a slight change from an imager. So here you have what I showed you earlier, an imager. The beams here are coming from the telescope, the blue filter, the detector. So for a spectrograph, what you do, you replace your filter with a prism or any optical element that split the light into its color. And then when you send the beam from one star at a time, you get several colors. So here, what you pay, your penalty for having a spectrograph is that you can only use one star at a time. While when you take a picture, you have all the stars in the field that you have the color. But here, what you have is all the colors. So you record basically the rainbow of whatever star you're looking at. And when you record these colors, this is what you get in the end. And this is what we call a spectrum. It means that it's the intensity of all the different colors of whatever object you look at. And what's interesting here is that there are dark bands. You see one very dark here. Dark here. These dark bands are due to elements that are present inside of the star. So here I give you an example. I just zoomed in on a part of the spectrum. So here you have this dark band here. This is due to magnesium here. And this one here, this dark band here, is due to iron. You have magnesium here, this sodium, sorry. And this here, the most abundant element in the universe, which is hydrogen here, has a darker band right here. So basically, this is how we know what makes up the stars that are around us. So we look at stars, we do spectroscopy, we can figure out which elements are inside of that star. And this is how we know, basically, that the physics in the universe is the same everywhere. We find elements in those stars that we find here on Earth. So there's no weird elements. There are places where we cannot identify the element, but it's all only a matter of time that we relate it to something that we can find on Earth. I can give you examples if you ask me questions about it later. So the last instrument that we have is called CITEL. So it's the latest instrument at CFHT. It is an imaging spectrograph. So meaning that you can take a regular image and you get a spectrum for each object in the image. So this enables unique science. And remember, I was telling you earlier, when you use a camera, you get just a few colors, but on all the stars in the field. When you use a spectrograph, you get all the colors, but just of one, or some spectrographs have a few stars in the field, but you're limited into what you need to do, you can do. So with CITEL, we can do all of it. We have all the stars that are in the field have a spectrum. All the elements, everything that's in the field, the stars, the galaxies, they have a spectrum. And that enables really unique and powerful science. So here's just an example of what can be done with CITEL. This is a velocity field of a galaxy. There are the blue parts that you see there here. They are coming toward us. And the red parts here, they're moving away from us. And the yellow and green parts are somewhere in between these two extremes. And this can be done with CITEL. It's a really powerful instrument. It's just one type of science we can do with it. Okay, some science that we do at CFHT with these instruments. So basically what I will talk to you about is dark matter, dark energy, which are really big enigmas for astronomers today, something we try to understand, but we don't yet. And also we're going to have a new instrument to search and characterize planets similar to our Earth, around red stars. So first I'll start with dark matter and dark energy. So basically the dark side of the universe. So the universe is dark and we don't understand most of it. So here's a pie chart of what we think the universe is made of. So you have 75% of the universe here, this green region, that is dark energy. So it's an energy that we measure indirectly, but we don't know what it is. But all we know is that it constitutes 75% of the total budget of energy of the universe, which is enormous. 21% of the universe here is dark matter. So again, this is something we measure indirectly, and it's called dark matter not to, be mysterious or anything, but because it's dark. It's non-luminous matter. A star, a galaxy, it's something we can see. It's luminous matter. The dark matter is something we do not see. It's non-luminous. We get it by using techniques that measure it indirectly, and I'll show you one of these techniques. And 4% here of the universe is normal matter. So this is what we know, basically. Normal matter is what makes us. It's in physics jargon, it's called the baryons. So the baryonic matter is what makes us and other types of matter, but it's basically what we know about the universe. It comes from the luminous matter, from what we can study here on Earth, from the stars, the galaxy, everything that we can see, we can characterize it as normal matter, and it constitutes only 4% of the universe. So we still have a lot of work to do to understand the universe. So that dark matter. So here I'm presenting to you one way to measure dark matter. So mass, it uses the principle that mass distorts light and produces arcs and filaments. And you can see them here. This is an HST picture, a Hubble picture. And you can see all these rings that seem to be around this center here. And these rings basically are produced by the distortion of space-time, and that was something that was predicted by Einstein's theory of relativity, is that if you have a galaxy here in the background, and you have some mass here, which in this case is a cluster of galaxies, several galaxies, all the rays that get close to the cluster of galaxies in front of the galaxy you're studying in the background will be distorted. That's what produced these arcs that we see in this picture. So using that, people use CFHT and megacam, because remember I told you megacam is a large field of view, so you can study a lot of galaxy, millions of galaxies at the same time, and you use that, you use this distortion idea to figure out how much mass there is in the center. And here, that's the blue part. The blue part is not a real part of the image. That's been added to the image. The real picture was just showing these yellow guys here. That's the luminous matter. The blue regions here, this is all the dark matter that we infer from the distortion of the rays. So you can see there's a lot more. So this is an indirect detection of dark matter. We don't know what it is, we don't know what it's made of, but we know it's there. And we can do that all over the place, and we see it everywhere. There's more techniques to detect that dark matter. That's just one here that I've shown you that is used at CFHT to detect dark matter. So dark energy, really quickly, it is measured by using standard candles, basically, or standard rulers. So I'll focus here on standard candle. So here, if you have a candle that you know how luminous it is, if you put it farther out, it decreases and decreases and decreases in luminosity. Its brightness becomes less and less. If you know how much light it emits, you can figure out its distance. So this is basically what we do, and we use supernovae. Basically, at CFHT, that's what was used. So here you have a depiction of how it works. You look at the same field, but at two different times. So 3 weeks before the supernovae, that's what the field looks like here. And then there's the supernovae discovery. And if you make the difference between these two fields, everywhere is zero because nothing has changed in luminosity except the supernovae here. So we have a theory where we think we understand what's the intrinsic luminosity of a supernovae. So we know how bright it is. So if we measure its brightness, we can know how far it is. So using that, scientists are able, that's again one of the techniques, but they're able to figure out that the universe is actually accelerating and there's something pushing it. And that something pushing it is a force that we call dark energy. So again, we don't know what it is, and we're trying to figure out what it is. So quickly, exoplanets. So basically, we're looking for life in the universe. Exoplanet is a field that is booming. So here you see the number of exoplanets as a function of time, the discoveries. So now there's more than 1,000 planets around other stars that have been confirmed in the last few years. So this graph here shows the numbers. So it's really something that's going up, and we keep discovering planets around other stars. The new instrument that will come at CFHT, it's called SPIRU. So it's a little similar to the spectrograph that I talked to you about, Espano, except that it goes in the infrared. It doesn't record optical light like you can see with your eye, but it goes in the infrared. And it uses a method called radial velocity to discover planets around stars smaller and redder than the sun. So the sun is a yellow star, and there's these red stars that are way more numerous than the sun. And this instrument will look into these. So in conclusions, that's my last slide. Science at CFHT goes from stars and planets in our neighborhood to very distant galaxies using 4 state-of-the-art instruments. And CFHT helps us understand the basic questions about the universe and planets around other stars. So I will stop here and take questions.
All right, Daniel, thanks for sharing with us a little bit about the instrument, CFHT. And, you know, it always amazes me how little we know. So, you know, one reason why we do these hangouts is we want to show students that there's so much more left to explore and discover. And I think that graph that you showed us, that we only know, or we can only see about 4%, and there's still so much out there we don't understand. I think that's pretty exciting. And exoplanets, you were saying we've discovered probably somewhere in about 1,000, but there must be billions upon billions upon billions, maybe just in our galaxy alone. So it's pretty incredible to think about that. Yep. All right, well, let's meet some classrooms, and let's grab a question from each to start, and then see how our time is looking. So our first group, let's see, let's go to Louisiana first. We have in Zachary, Louisiana, with Mrs. Gilpin. Let me turn your microphone on, and you guys can ask a question about the telescope. There we go.
What is the coolest thing that has been discovered with CFHT?
Let me think. We discovered several things. The coolest one, to my view, was a recent discovery using, again, this gravitational bending of light, but they used it in a different way, and they were able to measure the expansion of the universe, but in a completely different way, and it validated what had been done before. It's called the Hubble's constant, and it measures how fast the universe is expanding. And it was quite an interesting method where they had to, where they used, again, this gravitational lensing to figure out that constant. I thought that was pretty cool.
So that's interesting. We know the universe is still growing, it's still expanding and moving away from us, and so it's a rate, I guess. It's moving at a constant rate. Yeah. It's the same.
No, it's accelerating, but this measure measures the acceleration now. So the acceleration in the past might have been different. The expansion speed in the past might have been different. And maybe it will be different probably in the future, but it measures it at this time, at the time zero, we call it, which is now.
All right. Mrs. Kementi's classroom's joining us from Maunakea in Canada. They're a grade 3 classroom. Let me turn their microphone on. You guys have a question for Daniel about the telescope?
Hi, we do. We're going to ask a question about some of the scientists there. Can you hear us?
What kind of training do the scientists do at the Canadian-Francois telescope?
Oh, very good question. Thanks for asking. So basically, our astronomers here, our scientists, all have a PhD in astronomy. So basically, this is the highest grade you can get in universities. It's you do your high school and then you go to university and then you study physics for 3 to 4 years. So that's a bachelor's degree. And then you do a master's degree, and then you do a PhD degree. So we're looking at 10, 15 years of university studies. However, it's fun. I mean, if you like astronomy, this is something that's fun to do. You do research. So this is what requested for our astronomers. However, we don't only have astronomers that work here. We have engineers also, a lot of engineers actually. We have, at CFHT, we have 45 employees, and we have 8 astronomers, and all the rest of the employees are software engineers, mechanical engineers, electronics engineers. And these guys, they basically do, the minimum is a bachelor's degree in whatever field they're studying in. So and we hire a lot of those. So you don't necessarily mean, I guess my point is here, that you don't necessarily need to be an astronomer in order to be able to work at an observatory. There's a lot of people that we need to help us. Astronomers cannot do it all by themselves now, with all the technology that's needed and the size. You saw the size of the building. We need people to help us make it work. And these guys are really the ones that help us do science with the telescope. Good question. Thank you.
Great question. Let's visit Mrs. Akel's group in San Antonio, Texas. They're a grade 5 classroom. And I'll turn their microphone on like that.
How far have you seen through the telescope?
How far? So the farthest object I could find in the literature that was discovered with discovered with CFHT was about 12.8 billion light years away. So we can see really, really, really far away. Now the universe is thought to be something like 13 billion years old. So it may seem like we're right at the edge of the universe, but there's still a lot in this little gap between the 12.8 and the 13 point something, 13.5, I think. That's the age of the universe. So it's considered, it's not that far. It's far out, but in terms of what telescopes can do today, we're on the low end of it. Telescopes can see all the way up to 13, a little more than 13 billion light years away. So it's really far. It's really far out. So you guys know what 1 light year is, right? It's the time that light travels during 1 year. So light travels at something like 300,000 kilometers per second. So that's something like 5 or 6 times around the Earth in 1 second. So what we're looking at is 12 billion light years away. So it's the distance that light travels, not in 1 second, but in 12 billion years. So it's far. It's really far.
It's incredible to think of distances like that you can measure how far light would travel in 1 year, but then you can look over 12 billion that far. That's incredible. The distances. You don't think of distance that big when you're on Earth. You think of like the distance from a city to another as a big distance, but really it's nothing.
That's right. Yeah. Just to put it in perspective, the closest star to us would take 4 years to get to at the speed of light. So it's 4 light years away. So even the closest star is really far from us.
All right. We have a group in Montana, in Kalispell, group of grade 3 students at Elrod Elementary. Let me turn your microphone on. Oh, there you are. And you're on.
Do the stars that you study have similar temperatures?
Oh, awesome question. So no, they don't. And stars have a whole range of temperatures. This is something I didn't talk about, but remember when I was talking about the sun the sun has a certain temperature. It's an average star. But there are stars that have lower temperature than the sun, and these are redder. They're redder stars. And there are stars that have a higher temperature than the sun, and they're bluer, like the star Sirius. I don't know if you guys have ever observed it. It's blue. It's quite blue. When you look at it in the sky, it's blue. And it has a higher temperature than the sun. So basically, temperature is a very important parameter for stars. That's how we classify them, basically. It's a sequence of temperature. So from the coldest stars to the hottest stars. And the coldest stars are something like 1,500 degrees. And the hottest stars can go to 100,000 degrees. And the sun is about 5,500 degrees. So temperature is an extremely important parameter in astronomy. So thank you very much. Thanks for asking. That's a great question.
That is a great question. It's different than you'd think. You'd think here on Earth, we mark things red as hot, but it's the opposite.
That's right. That's correct.
Red is colder in space and blue is hotter. That's cool.
Yeah.
All right.
Hi, do you have a question? Hi. You ask your question. Go ahead.
What are stars usually made out of, and what's the biggest star that you've found?
So she's asking, what is the big? Did you hear? Okay.
Yeah. What they're made of, and what's the biggest star?
Yes.
Okay. So another awesome question. So apart from temperature, what the stars are made of is another extremely important parameter that astronomers look into. So remember, I was telling you, when you have the spectrum, there's these lines, there's these dark lines that are elements that are in the star. So what we do, we count how many elements there are inside that star, and we know what it's made of. And basically what's happening is that we know what the sun is made of, and we know that there are some stars that have 1/3 of the elements that are found in the sun. So it's made of less elements than there is in the sun, and then there's stars that have more elements than what is found in the sun. But the elements themselves that are found in the sun, they're the same. It's the periodic table, all the way up to iron, I think, is found in stars. So it's a very important parameter, just like temperature. It's how we classify star. We call it metallicity. So the metallicity, the amount of metals that are found in the star, is what tell us what it's made of. So great question. So the other question, the biggest star, last I heard it was I think the Pistol star, which and it was recorded to be 120 times more massive than the sun. So like temperature, we refer everything to the sun. Like elements, we refer everything to the sun. Mass also, we refer everything to the sun. So there are stars that are less massive, more massive. The biggest one, I think, was 120 times the mass of the sun.
So Daniel, just to put that in perspective, off the top of your head, how many Earths would fit inside the sun?
Oh, so it's thousands of Earth fit into the volume of the sun. So I don't know the exact number from the top of my head, but it's thousands of suns, of Earths that fit inside the sun.
It's amazing size comparison. You can have thousands of Earths in our sun.
Star is way bigger than the sun, so you can have hundreds of thousands of Earths that fit into that.
Amazing. So much we don't know, and so much. You can't even contemplate the size sometimes. Let's see. There's Mrs. Murray's group, grade 9s from Brockville, Ontario. Let me turn your microphone on for a question.
Yeah. What's the difference between dark energy and dark matter?
Oh, okay, thanks. Good question again. So dark matter is literally matter. Is if we knew what it was, I could have dark matter right here next to me and grab it. If that were the case, it's matter. It's something solid. Dark energy is more like a force. So like gravity is a force on the Earth, and it pulls us down. So, but I can't really grab gravity, right? I feel its effects, but I can't grab it like I grab matter. So dark energy is a force, and it's a force that pushes outwards in the universe. So gravity pulls us toward the center of the Earth. Dark energy pushes on the universe, but outwards, and makes it expand faster, basically, the universe. So if you have an acceleration, you gotta have a force. Remember, you know, when you're in a car, and your mother or father brakes, you feel yourself being pushed forward, right? That's a deceleration, and there's a force associated with it. Same thing when you accelerate, you get pushed back. And if you go at a constant speed, there's no force. So the fact that there's a force that pushes on the universe makes it accelerate. So that's the main difference between dark matter and dark energy. Dark matter is really matter. It's something we can grab. And dark energy is a force.
All right. Another great question. So great questions from all of our classrooms. And it was great to have you guys joining in today. So we're at about the 45-minute mark, Daniel. So that's unfortunately usually when we wrap up. But again, I have to thank you for taking us into the control room and giving us a little peek at what you do. Maybe just before we wrap up, can you briefly tell us a little bit about some of the screens we're looking at? Looks like maybe a weather screen behind you.
Oh, sure. Yeah, thanks for asking. So here behind me, you have our remote observing room. And up here, these are mainly weather screens. Observer at night uses to figure out what the weather is on the top of Maunakea, and also what's coming. So is there some bad weather that's coming? Because the telescope instruments and the optics, and they're all very sensitive to high humidity. So as soon as there's a little bit of rain, or if rain is threatened or humidity rises, then our operator is instructed to close the telescope. And those screens over there, yeah, there they are. Yeah, those screens there, there's one that's black. Light them up. So this is where they spend most of their time. So they basically collect the data using these screens. So they're connected directly to the instrument, and they send an exposure. The telescope will move to the target, and then it'll acquire the data and read it out, and then they'll look at it and tell us and see what's going on, if the exposure is good or not, and then they repeat that all over the night. So they use these screens here that are right there to do that.
All right. Well, Daniel, once again, thanks so much for hanging out with us today. And if
welcome.
classrooms wanted to dig a little deeper and find some of the images maybe that have been taken from CFHT, can they find some of those on the website?
Yes, they can. So actually, if you go to our website, there's an images tab, and we have an image of the month. So, and then if you go there, you can have electronic versions of these pictures. They're all very nice pictures, and we've been doing that in 15 years. So, and they're all on the website, categorized by year.
All right, excellent.
So the website is cfht.hawaii.edu.
Perfect. Well, again, Daniel, thanks so much. And classrooms, thank you for your awesome questions. I'm going to turn the microphones on and give you a chance to say goodbye and thank you to Daniel. And then we're going to sign off for today. So again, thank you, Daniel, and I hope you enjoy the rest of your day. I'm sure it'll be a nice one.
I will.
All right, microphones coming on, classrooms. Goodbye and thank you, and we'll sign off for today.
Thank you. Goodbye.
All right, thanks everyone. Thanks. Daniel,
Bye.
and we're signing off.